This presentation is titled Number Theory, Neat Examples, Set 2. My name is Anton Antonov. Today is March 30th, 2025. In this presentation, we are going to feature a Raku package for doing number theory. We're more precisely discussing prime indexing, modular exponentiation, and inverse. So what are neat examples? They're straightforward code that produce compelling visual and textual outputs. They showcase the programming language in focus, in this case Raku, and different Raku modules. I'm going to use the package math number theory for the number theory functionalities. The visualizations are done with JavaScript D3, also with the package graph, not so much with the graphs themselves, but the visualization functionalities in the package graph. And in the previous presentation, I did not mention that Raku actually has quite a lot of built-in number theory functions, like is, prime, mod, and so forth. I have extended those functions and provided many more from number theory perspective. For example, the GCD and LSM, the greatest common divisor and least common multiplier, they have been extended to work with rationals and Gaussian integers. The extension is in this math number theory. All right, so first we're going to discuss the prime subroutines from that package. So if we have a list of integers, we can use this hyper method call operator, right, to give the corresponding primes. So the 10th prime is 29, the 20th prime is 71, and so forth. So compared to the previous presentation, I have extended the signatures of prime, also next prime, and some others to use lists, right? So instead of using this very neat Raku idiom, we can use prime and a list of numbers, produce the corresponding primes. The function next prime gives the prime after the argument. It doesn't need to be an integer, the argument of next prime. Also, we can provide a second argument, which is in this case is going to give me the third prime after 33, which is 43. So again, this has been extended to work with lists on both locations, the first and the second argument. So here we can showcase prime, for given index in this way. Let's actually visualize the prime gaps. So this plot shows here the gaps between the primes. So on the x-axis we have this prime indices, right, and the y-axis are the gaps. You can see I'm taking the consecutive primes and looking at the difference and plotting the gaps. All right, this is actually a very big topic, and I'm not going to expand anymore further here. So let's actually look into some other prime functions. Twin primes, these are pairs of primes with difference between them, which is 2. Similarly, cousin primes with difference 4, and sexy primes with the difference 6. Sexy is inclination or inflection of from Latin. So here we can visualize the twin primes using Coulomb spiral. Coulomb spiral is very fruitful kind of way to visualize primes or any other kind of functionalities from number theory. I like this kind of smearing effect, like motion effect kind of, which is happening here. Let's remind what the Coulomb spiral is. So we basically take the prime numbers and we put them in a spiral. So if I look into this spiral lattice is a built-in function of number theory. So we can see, we have the spiral of numbers. We can also filter out the composite numbers and get this Coulomb spiral, which manifests these diagonals. I have featured the Coulomb spiral in the previous presentation, also with the spiral lattice. All right, so modular exponentiation. So it's defined in the following way. We have a number a, we exponentiate it with another number b, and we find the residual, the remainder, by dividing by m. So exactly how it is in this formula, the order of these three numbers, they appear in power mod. Power mod is an extension of exp mod. Exp mod is built in Raku. Power mod, though, works on Gaussian integers, and I have changed it to not complain that much in order to be more convenient for certain computations, like, for example, making neat examples. Power mode name is after the power mode name of the function in Wolfram language. In general, I'm using the Wolfram language number theory functions for, quite a lot of inspiration, both for functionalities and signatures. And of course, I change those names and signatures to fit Raku, to fit the Raku styling. So here power mode is being demonstrated to work with Gaussian integer. Gaussian integers are complex numbers with integer real and imaginary part. So here this complex number is exponentiated to 2, then mod 3 is being found. So let's actually show some examples here. Again, I'm using prime, all right, and so these are indices or indexes for primes. I'm picking randomly one of these indexes, finding the numbers between 1 and the corresponding prime minus 1, and then I'm using power mode. So 3 is being exponentiated with the numbers here iteratively, and then we find the remainder by dividing by the corresponding prime of the index. Some of these are very nice. I would say probably this is the nicest. This is the first which actually I think I produced. All right, so we can also do the following visualization, which I was using randomly at random. I was making in the beginning of the presentation. So let me explain what's going on here. So we take the numbers between 2 and 100 and make the Cartesian product. Then we find the power mode. So we get a list of lists with length 2, right? And so we take the first element of each list, exponentiate it with the second element, and find modulus of 32 in this particular case. Since this is just a list, I need to make it a matrix in order to use matrix plot. That's why I'm using rotor here. All right, so again, we can use the Ulam spiral or spiral embedding, spiral lattice. And this here, if we are not using, say, if we're using a different color scheme or color palette, the spiral might not be obvious. If I use any kind of cyclical color scheme, the spiral is going to be obvious, more obvious. You can see here how the spiral goes. Probably using different numbers, we can produce different patterns here, right? Sometimes the spirals are manifested, sometimes not. I'm going to return to rainbow here, and I'm going to return to the original numbers, say 3 and 17 here. All right, so let's discuss modular inverse. It's connected to power mode. In general, one of the most important mathematical concept or constructs in number theory, especially in algebraic number theory, is the multiplicative group of integers, modulo n. So here we have the modular multiplicative inverse of a, modulo n, defined in this way. We are looking for the number b, which multiplied by a mod n gives 1. So this is an inverse element in that multiplicative group of integers I was mentioning. For not all pairs of numbers k and n, modular inverse exists. They need to be co-prime. And if they are not co-prime, modular inverse, the function of this package, returns nil. And so you can see here in this table, actually before going with this table, you can see how modular inverse is like a shortcut of power mode. So if we have in power mode the second argument to be -1, this is equivalent to modular inverse. So here this table shows how for different numbers, what are the modular inverses, and you can see, say for 4, if we look into the number 2, which is not co-prime with 4, we basically cannot find the modular inverse, right? Modular inverse exists only for 1 and 3. All right, so let's actually visualize some patterns based on existence of the modular inverse. So here in blue, the points correspond to the points which do not have modular inverse. So I have this example, I have picked the modulus, one of this 12, 14, or 20. I have picked the size of this rectangle, so basically, and then I'm applying some formula with the modular inverse, trying to see does this modulus, like, does the modular inverse exist for the picked prime? All right, so pretty simple. If I use some other number, this might be like, say, if I use a prime, this might be actually quite boring in a sense, right? So less interesting, and so that's why these numbers are being selected. Next, I'm going to discuss sunflower embeddings. This is a built-in function now in math number theory. In the previous presentation, I was also using sunflower embeddings, but right now this is built-in function, so you can see it here. So sunflower embedding takes the first argument, the total number with which we are going to, of integers, we're going to do the sunflower embedding, and a function. This you can give a name argument, which is a function. How do you color, or how do you, what do you do with the numbers which are placed, which are embedded in these sunflowers? So this more or less what is happening here. If I use larger numbers, I'm getting kind of smoother results, maybe produced in a slower manner, right? Even larger numbers can produce smoother but somewhat smeared results. So I think the best one is this, which is somewhat grainy or choppy, but in my opinion looks very nice. I think for 68, the best one is actually with set 1. So this is really neat. And so yeah, here, if I didn't mention this already, we're looking actually into the existence of the modular inverse, right? So modular inverse, if it exists, I'm taking the minimum of the modular inverse and the actual number mod p in order to kind of not to proliferate too many classes, so to speak, in this embedding, to reduce the number of colors being used. So yeah, pretty nice in my opinion. So next is chords visualization. This comes again from the fact that multiplicative group of integers modulo n is a very important construct. Modular arithmetic is very important in number theory, and because of this, circle chords visualizations fit very well quite a lot of properties or interesting relationships in number theory, especially based on modular arithmetic properties. Graphs and graph plots can be used. This is what is demonstrated here. I'm using the wheel graph. The wheel graph has a hub in the center of the wheel, but I'm removing it in order to just get the numbers from 1 to whatever size here n. I have taken. This is not necessary, but it is kind of neat that I can use the package graph to very quickly produce some visualization. This is the first visualization I did. Actually, let me show you what these are. So here I'm going to evaluate this, going to show some of these circular embeddings. Since some of these are slow, I'm going to start these computations. I'm going to describe what's going on here. So again, this is using the package graph. I'm taking the points between, say, 1 and 130, or 1 and 260. And if the inverse between two of these points exists, I'm drawing a chord, right? So pretty simple. They're not that pretty for small numbers here. Somewhat prettier results can be produced if we use orthogonal edges. For whatever reasons, this Jupyter framework doesn't always visualize this plot. So once it visualized it, it's for the same formulas here, for the same numbers, and you can see actually 131 looks very nice. But apparently, some problems with the renditions here. Anyway, instead of using SVG and HTML visualization embedding, which I'm doing here using graphs, I can use JavaScript D3. This is what is happening here. But before going to that last example, here you can see that if I use larger numbers, I start to have nicer embeddings. And some kind of very complicated patterns can be seen. It is much faster to use this JavaScript D3 visualization. There is a built-in function in math number theory called circular chords tracing. Again, the first argument is the actual number, say one of these 2000, 4000, whatever, right? Which are the numbers which are going to be placed in a circle. And then the second argument, or the named argument width, you can give it a callable, you can give it a function which says or tells how to draw the chords, right? In this particular case, they are pairs. And so yeah, this is what is happening here. I can say that these look pretty nice. They look like mandalas, but probably they're even neater than mandalas because they actually correspond to some numerical artifacts, so they have some kind of absolute neatness in them. All right, this was it. Thank you for your attention.